So last time there was a question about this control Z gate in ion trap computation. I will clarify um, that part first, but let me just tell you that this two gate or the 2-qubit gate is an important part of implementing quantum computing in different hardware. So in different scenarios, they use some specific property of the hardware to find a suitable uh, dynamics for it. The 1-qubit part is common. It is just rotation in some field, and you can do it in the Euler-Engel scheme and doesn't matter too much when you jump the hardware. So the first thing which I described was what is done in NMR. So NMR, there was a 2-qubit coupling, and you are using that 2-qubit coupling to implement this gate. The caveat was that that coupling was always on. You can't use it like a pulse, etc. So you use it for a finite pulse, and then you have to do all the refocusing and cancel all the other unnecessary stuff which comes with it. In these other hardware scenarios, you have the flexibility to introduce the 2-qubit coupling for a finite duration. So you can apply pulses of some duration. You do that operation, and then you can switch off. Okay. So that is what is done in the proposal which I mentioned last time, and I gave you a table, but the question was that there was a specific pulse which could take G1 to E0, but not E0 back to G1. Okay, how is that possible? And certainly it cannot work with the same state. So there is a caveat inside there. And the caveat is that the pulses use laser polarization as an extra degree of freedom. Okay. It's available. There are two polarizations of a laser light. And means say the computational space is made up of G and some excited state, which can be obtained by absorbing a laser pulse, but there is an E prime. The second polarization is there, which is not part of the computational space. And so the job is to exploit this extra state, which is not part of the computational space, but as a virtual intermediary. Okay. So there are three pulses. So pulse, the pi pulses, which are steps 1 and 3, use the first polarization for this state E. Whatever it does, it basically is a what you call population interchange. G will go to E and E will go to G with the pi pulse, but the 2 pi pulse, which is in step 2 of this protocol, it uses polarization for the state E prime. And the consequence of that is that the state which I called GG1 in the table last time, I'm not going to write down the whole table again, or it changes its sign, but in order to do this, it goes through the intermediate state, which is E prime. It's a different polarization which is used. But the other state, which I had called GE0, remains, or rather it remains unchanged. It cannot become this E0 cannot go back to G1, some intermediate step with overall sign getting flipped, because the laser is tuned to go through this particular polarization. And this is a useful concept, so you have to know a little bit about quantum optics to figure out all these tricks, but that is how the gate works. And there is a little generalization which is pointed out in Nielsen and Chuang's book, that for control Z, you need to flip sign of the 1-1 component, okay, in computational space, which is well, all the 4 combination, and you can do it by using some state which is outside this space. So any state coupled to 1-1 and outside this space can be used to flip sign of 1-1 by the same 2 pi pulse. Going to come back, but so you can label this state whatever you want. Say I will give some label. It is different than the 0 and 1, so let me call it something which can couple to 1-1. Doesn't matter what it is, but it has to be consistent with whatever selection rules you have in the system. They call it 2-0. 2-0 will couple to this, but it won't couple to any of the other ones, and then you apply a 2 pi pulse, so it will only have sign flip for this. It won't couple to this because all the states are different in energy, and so you can apply a transition selective pulse which will couple this and this, but all the other one have wrong transition energy, so they will not work. And this can be done in other scenarios, for example, in this superconducting qubit systems where there are extra states available. You are just using the lowest two levels, but extra states are there. You can use one of them to cycle through and implement this control Z gate. So this is a procedure, but yes, the part which I missed was that didn't take into account the states available outside the computational space, but you find uses for that as well. Okay. So now let me get back to this neutral atom quantum computation. It has yet another trick to implement this 2-qubit interaction and the control Z gate, and that depends on what I mentioned last time, the existence of Rydberg atoms. So the Rydberg states are not used as any of the ground state, but they are used as virtual intermediate excited states. So and the important point of intermediate states are that they don't have to survive very long. They have to survive only for the duration of the pulse. Ground state has to be stable. It has to be there for long time, and there you need long coherence times and all those kind of properties. But this intermediate state can live with shorter coherence times as well. And that is important because last time I mentioned that there are decays which you cannot avoid. One of them is spontaneous decay of these states. So that can be as large as order of second, but that other part which is a 3-degree background radiation coming from whatever cosmic wave environment available everywhere. This is much shorter, and this you have to calculate it explicitly and under certain assumption that for this h nu particular region where even when you cool down the atoms to very low temperature, this is something can be avoided. You make this below Kelvin or millikelvin or whatever it is. That is why this um, condition comes from. This is the atomic energy transition frequency, and this is the background. And you can make the system very cold, but still this will produce a decay rate, and that time turns out to be of this order. There is not much you can do about it. And this is generically true. I mean, it's true for Rydberg states, but it will be true in other physical realization as well, like again the superconducting systems. You are not going to get rid of this black body temperature. So you have to keep in mind that, well, these excited states, whatever they are not going to live very long. They will live at the most a millisecond, and whatever you want to do, you have to finish in that particular job. Then you come back to ground state. The ground state can survive for a longer time, but the excited states are not going to survive very long. Okay. So now comes various other parameters, some of which I mentioned, but I will repeat that what do you need, etc. So one can suppress errors, or basically it means by high vacuum and low temperature. Why high vacuum helps? Because one of the sources of the errors in this atoms traps are just collisions between atoms. And if you make high vacuum will avoid collisions, and many times it is enough that if you make really good vacuum, you don't have to worry too much about temperature except for this black body stuff which you can't get rid of anyway. But the other part, you can have these systems in just tabletop experiments at room temperature. The high vacuum takes care of everything else. So that is a yeah.
So in an experiment, then what is the black body that is causing these photons? Is it the environment?
It's the environment. Yeah, it's the cosmic microwave background radiation. It's all over the place, and well, it came with the universe, whatever it is. So can't get rid of it. There is no way to shield or filter or anything like that. But what you need to do is still go down to sufficient low temperature to be able to trap the atoms. Because what does temperature specify for kinetic theory of gases? It's a measure of the velocity. So the atoms are moving very fast at room temperature, and you just cannot trap it like that. So to be able to trap, you have to reduce the kinetic energy so that they can be remain confined in whatever the domain you want, micrometer size region. So So here are now very sophisticated techniques to trap the atoms. They are all based on electromagnetic systems. So, well, there are names for it as what are called magneto-optic traps, and sometimes the other word is used is laser cooling. Uh, so, what is done is you are reducing the kinetic energy of the atoms. So, kinetic energy of atoms reduced by one of the most common technique is known as Doppler cooling. So, it uses again this pulses which are shifted from the absorption frequencies, and in this particular case it's a red shift. So, Doppler effect, as is known classically, is the frequency seen by the atom is larger if it is moving towards the source, and it is smaller for the in the situation where the atom is moving away from the source. So, what does Doppler cooling do is you shine a light, there is a collection of atoms which are all moving randomly, but those which are moving towards the laser source will be able to absorb the red shifted pulse, because the pulse's frequency is little less, but it's moving towards it, so it sees the higher frequency and it's able to absorb it. The simultaneous consequence of that is that a laser pulse not only supplied energy, it came with a momentum. Photon has a momentum. And so it's the atom is moving towards the source, but the momentum is going the other way, and it absorbs the photon, momentum reduces. So it was moving towards the source, now it will be reduced in velocity, and the other atoms which are going in the wrong direction, they are not absorbing anything, so their momentum will remain whatever it is. But the ones which are moving towards the source, the momentum will get reduced. And of course, this has to be done multiple times because every photon has very little momentum. The atomic kinetic energy is generally much bigger, so can't do it in one shot. So the atom which absorbs the photon is gone to some excited state, it will radiate. But that radiation is isotropic. It is not going back towards the source, so it will get a kick by the radiation, but it will be random. And so you keep on applying these multiple kicks, and it will slowly reduce the momentum of the atoms, and then you have to do it in 3 dimensions. So you use actually 6 lasers, 1, 2, 3, 4, etc., to cut down all the components. All of them are these red shifted pulses. And so the atom gradually cools down and gets trapped. So, well, 6 lasers in 3 dimension, cut down the momentum. By repeated absorption and isotropic emission of photons. Yeah. Hmm? Redshifted pulse are the pulses with energy little bit less than the transition energy. The same kind of thing I mentioned together with the Raman effect in the last lecture. Red means little less, blue will mean little more. Okay, so this was actually a major achievement to be able to do that and bring down the atomic velocity, so they actually end up getting trapped. The trap part I have not discussed, but reduced the energy sufficiently smaller magnitude, and this is okay, same method is used for another well-known demonstration, which is this Bose-Einstein condensate. It was known that this condensate would form at low enough temperature. The question was, how do you get there? And it was demonstrated by this sophisticated laser cooling method and all this Doppler effect, etc., to reduce the velocity. And of course, when it was demonstrated, etc., the people who did that got the Nobel Prize for being able to do it experimentally. So this is an important technique, yeah.
Is this done continuously once the atoms are stopped?
Once it is trapped, and because of the high vacuum, they will remain there. But you have to bring it down. So you start somewhere which is a room temperature gas, and then go down slowly, step by step, all the way.
So the emission part, is that simulated or spontaneous?
No, emission will be spontaneous. I mean, when it absorbs, it will absorb from the specific laser direction, but emission will be isotropic. So that is why this directionality is not there. It's uniform in all directions. So yeah, sometime it will be ineffective as well, but you have to keep on doing multiple trials till you get there. Okay. So this is well, one part of the story, how do you make a trap, and the next part is actual description of the trap. And yeah, and again, because of the what you call properties of what are all the energy levels available in various different elements, most of these experiments are done with heavy alkaline or alkaline earth elements. Okay. So whether it is Bose-Einstein condensates or this Rydberg atoms, they use this atom, but that is because of their particular energy levels which are available. And these are like rubidium, cesium, strontium. Those are the elements which are appearing in all these experimental devices. Yeah, dealing with all the hardware, you need to know properties of elements in the periodic table. That is what is available, and you have to figure out which one is suitable for doing what kind of things. Okay. So now comes a description of the trap, and those are something which go under the name of optical tweezers. Okay. And what they are focused laser beams on dielectric objects. Dielectric means that when you apply electromagnetic field, it will get polarized. Okay. And that polarization plays a role in the focusing. So, so how does it work? It's a typical scenario where the laser beam is represented by a kind of conical front. That is the meaning of this focusing. You start with an initial distribution, you narrow it down, doesn't go to a point in quantum theory, and it will go and then it will spread out. The purpose of this is that the narrow region, the intensity is large in the what is called a neck of this particular field. Now, what does the polarization do? The energy of a polarized object is the dot product of the polarization with the external field. Okay. And it's minimized in the lowest energy configuration. That means the atom is kind of forced into this narrow region where the intensity is large. So, what I can write is they are not atoms, they can be objects. But that is not the whole story, that you can force it about this direction. What about the third direction? Okay. So, third direction you have to create a balance, because there will be a situation that yes, it will try to say remain in this region, but it will not be as much localized rightly at the center, because there is gravity. Okay. So the gravity will actually try to make it fall down. But once it falls down, the intensity here is lower, so this dielectric force will kind of push it up other. And the reason is that the atom gets localized not at the extreme minimum, but little bit below. And that is the effect of gravity. At the some part of this focusing but there is an equilibrium somewhere you can get with all these various forces, and then the object remains stable, provided it is cool enough. Okay, because this is just an equilibrium equation, you are not taking into account all the velocity. You have to bring it down the velocity so much that whatever this potential is produced over here, it can't escape from that. And these traps or the tweezers are used for not only atoms but also bigger molecules. All you need is a dielectric, and much more than that, things like bacteria and viruses, they can also get trapped inside this. And that is actually a very important technique for studying molecular biology. Okay. Can't make it too big, or you can put even some small living cells inside this as well. Well, living or not, maybe dead, but etc. The limit is it's up to micron. It works up to about a micron size. Atoms are, well, molecules are nanometer size, so much smaller. But micron size is where all these viruses, bacteria, some cells, etc. Exist, and these traps work even in that particular region. So the tweezers are a very important tool for studying all these kind of things. Okay, and now you have a situation, you cool down the atoms so that it got trapped, and then you can make there can be and you have the sophistication to make a lot of this, just arrange the array of these traps at a separation of the size about 10 microns. And so you are not restricted to just a linear chain of a register. You can actually make a two-dimensional array or even a three-dimensional lattice. And put all those atoms in this arrangement, and that is something which is an advantage for scaling the system. You are not just making one-dimensional chain, you can make a large collection. What the frequency of lasers? Yeah, but the point is that there will be a lot of other lasers which will be causing various transitions, but they are typically in the radio frequency range, while these ones are optical. So yes, there will be small perturbations by all the various pulses which you shine, but they are not going to knock out the atoms from these particular steps. All these lasers are optical, high frequency light which has enough energy. Yeah.
The Doppler cooling is used for gaseous substance, right? They are moving in random fashion that we are here.
Yeah.
Alkali atoms are usually observed in metal state. How does those work?
They can absorb some laser from the ground state to go to some excited state and then radiate that energy back. Those transitions will be there in all of the atoms. See, Doppler cooling has to use a transition with some redshifted pulse.
Aren't we confining them spatially in this method? We are confining the atoms spatially, right?
Yeah.
But if alkali, if you are using alkali substances, they are already metals, so they are already fixed in lattices with some vibration.
No, but they have their internal energy states. This is not the vibrational energy. This is the electronic energy. If you take some atom like cesium, it has multiple energy levels, internal energy levels, not the vibration, rotation kind of stuff. And it will absorb energy for those internal levels. That is what is used here.
These are vapor states, right, of these.
Yeah, they are all gas. It's an individual.
But then we have to put it in high temperatures, right, to get them in vapor state. How do we, if they are in vapor state, then the temperature should be very high. How do we
No.
they're metals?
Dilute gas. You can make all these things, individual atoms, very dilute gas. Depends on the density. That's pressure itself does not dictate everything.
In this case, focused laser can itself disturb the atom by exerting certain momentum.
Yeah.
So that momentum is not disturbing the equilibrium position.
Yeah, so this is a perturbed and classical electromagnetic analysis just to find out what is the ground state, okay, of the polarizable objects. And yes, there will be continuous perturbations. That means whatever the object is trapped, it will jiggle around a little bit. It's not going to be completely fixed. But the point is that you can make these traps so that jiggling is small. There will be continuous scattering or absorption or whatever you want to call it. The atoms are not going to remain stationary, but those oscillations or whatever it is, they remain bounded, or rather they can even be measured, and that will characterize the quality of the optical tweezer or the trap or whatever it is, how good a system you can make. But yes, these are sophisticated devices, but people have been able to make them. Okay. So various things one can do in all these multiple geometries. I can point out a couple things which are quite common. So sometimes one of these things which is technologically helpful is that we are going to introduce some interaction lasers after having dropped all those things, and it is kind of easy to slide these traps around rather than move that interaction laser. And the same thing is used for the trapped ion case. It is also used for these neutral atom traps as well. It's just more convenient to do that because of the bulky setups, and this generically is, slows down the quantum operations, because you need time to slide the whole thing back and forth. You want to apply one operation, then you move the trap around, then you apply another operation, etc. But that is one feature which is quite commonly used. And other important point is that the so this is one caveat, whatever it is. That you made all these traps, but then you have to take this atom one by one and put it in the right place, and it has to stay there. Now this procedure is not perfect. That means sometime it will get trapped, and sometime that place will remain empty. And success rate is only that much, about 1 part in 2. Half the time it will work, half the time it doesn't. And so what you have is this array, but there are a lot of vacancies because things did get trapped. So what is done is now a extra jugglery with all the classical control system, that you work in this so-called occupied space as this is completely software. You have to measure that. I will come to it a little later, which places are occupied. And there is a completely software mapping which defines a subspace which you are going to use as a register as this particular location from the array.
Are we keep sending items until all of this
Well, that whole thing doesn't live that long either. So you work up to a certain stage, and then the rate of putting a new one in place and something else falling out, you kind of reach saturation. That is where this success rate is kind of 1 in 2.
How is the observation when it's occupied?
Yeah, so I will come to that. So that now brings the question of measurement. Okay. So measurement is by fluorescence of atoms which means light is shown on the atoms. It will absorb it, and after some time it will re-emit it, and you cascade that whole process many times, and you will have enough number of photons so you can see. The point is that in these tweezers you can make the fluorescence so that it is visible with your own eyes. Don't need a sophisticated detectors for small number of photons. It's visual directly by eye or camera or something like that. And that helps a lot. So you can actually see um, this trap you made, you put some atoms inside it, you take a picture of it. Okay. And then you know that these are the ones which are occupied, then you give it to the software and it will say that this is the register I'm going to work in.
In this case, to go the fluorescence state, shouldn't they be well separated from the sorry?
Hmm?
In this case, shouldn't the fluorescent states be well separated from the number states we're using for operations?
Yeah, so you can make it more sophisticated. So now this is just to decide the existence of atoms, that whether it is in this location or not. But you also want to make quantum measurement. So the quantum measurement requires that there will be at least two states of the atom, and you should be able to distinguish them. Okay. So what is done is not too complicated. You know there are two energy levels, and you select the lasers with some specific frequency, so it will knock off one particular level completely out of the trap, while the other one, the frequency doesn't match and it will remain there. And then you observe whatever is remaining. So by doing that, you will have a specification saying that these many of the atoms were in, say, the state 0, and the other ones were in state 1. This also has to be done, and this is actually the what you call limiting process in terms of the fidelity. Okay, so I wrote down some number. The software mapping actually you can do quite well, but this one has a fidelity of this measurement is about 95%. Nobody has been able to make it arbitrarily large. There is some inaccuracies which will remain.
This observation is also done using the fluorescence method.
Yeah. Okay. So now I can come to the actual quantum operation. Okay, this is just to define the atomic system and how it is arranged in space and what you are going to do for selecting various options here and there. And now the final part, which is quantum operations. So you need the two states. So the qubit states are the same as in many other situations. The hyperfine energy levels, which has transition frequency in the RF spectrum. And the 1 qubit operations will be done by the same radio frequency pulses which change these atomic states. So single qubit operations by this same Euler angle rotations. The main job is to now devise a scheme for 2 qubit operation. And here now comes all these properties which I mentioned for the Rydberg state. 2 qubit operations use this Rydberg states. See, the hyperfine energy level are actually much lower states of the atoms in terms of where the electron is compared to the nucleus, and the Rydberg states will be now going to some high atomic orbit with radial quantum number of the order of 50 to 100. But they will all be used as short intermediate states. So they are not going to sit there for very long. And how does this Rydberg state help in this whole scenario is that a new feature appears because of the large size of Rydberg atoms. So the hyperfine energy levels are very low. The Rydberg atoms are much bigger. But when you move the electron from this hyperfine level to a large level, so what I mentioned in the last lecture is that it will have a large dipole moment. It is away from the nucleus by not a distance which is of the order of nanometer, but it is micrometer. and because its size is large, there is a Coulomb repulsion between electrons in neighboring trapped sites. Elect- and this phenomena is known by a specific label. It's called Rydberg blockade. This Coulomb repulsion is actually fairly strong. The distance is of the order of micrometer, and so you can't put neighboring atoms simultaneously in Rydberg states. One will go there, the other one, if it tries to go there, it will get knocked out. And this prevents this kind of excitations, though by neighbors it will be dependent on all the geometry about who is close to who, and that has to be taken into account. But this is a feature which allows you to implement the two-qubit operation. This is where the two-qubit interaction is. That on neighboring atoms, you cannot have simultaneous excitation. So remember, all these states were like this, 1, 1 in a control Z direct. You needed simultaneous things. And this is a physical input which tells you that yes, something can be done if you manage the operations in the correct order. And remember that we have to use this Rydberg state as a kind of intermediate. The logical states are going to be back in the hyperfine energy levels, and you will use this stuff as a something which is virtual, or in some manner it is outside the computational space, but you can use it to implement the two-qubit operation, and then you come back to your logical space. So now I can give the sequence of operations which do this two-qubit stuff. There are other small caveats which actually allows you to do a quantitative specification of how large this Coulomb repulsion is, to make sure that this is a what you call, in some sense, a hardcore atomic gas. You can't get the two things to come next to each other, and this radial quantum number, why such large values are used, is precisely because of that reason, that you want this blockade sufficiently large. Okay. So remember this effective radius was proportional to n square times the Bohr radius size. So the dipole moment is order n square, and this repulsion is now kind of dipole-dipole interaction, which is order 1 raised to 4. Okay. So that is the size of this Rydberg blockade. You want it to be sufficiently large, so prevent these multiple excitations, and that is why you go to some sufficiently large quantum number. But you need to make estimates of all the numbers, how large or how small you want or some things to be, or how much you can tolerate. It becomes part of the scheme which will realize this control Z gate, because it is exactly the state with multiple excitation. You want to do something about it. I will write down the algorithm which does that, but that's where it comes in. So this magnitude of Rydberg blockade decides choice of this quantum number n, and also range of interaction in atomic array. Generally, it's of the order of two to three lattice sites. Doesn't have to be only nearest neighbor. You can say that I can have it a little larger, so not just one neighbor, but many neighbors in the array can simultaneously get excluded. But you are choosing parameters to do all those things in a clever manner. Okay, there are some other caveats which is this Rydberg excitation energy is many times quite large, and in terms of whatever optical lasers you have available, so you reach it in 2 steps. People have done all this jugglery. So the computational spaces is hyperfinite. This one is too large. You can't go all the way in one step. Maybe you go it in 2 steps. That's all right. Then one more caveat is that another trick. So the Rydberg atom, the electron went up by a large value of n. That means its binding energy is now very small, 1 over n squared. And the consequence of that is they can get knocked out the trap. So what is done is actually the traps are actually switched off. You do fast operation with the Rydberg state and then you put it on again. And hopefully that is fast enough so the trap is off, but the atom has not moved very much. Whatever it is, and it all can be managed. So as I said, all this machinery requires whole bunch of software which looks after everything, where the atoms are, how long they are going to be. It's all controlled online at a high speed, and it's all classical peripheral systems, but you can't do without it.
So,
Yeah.
this like, do we not want that optical like wheel that is holding it to knock the electron out of the ring?
Yeah. Because there are all this other stuff is there. As I said, the atoms were not stationary. They were jiggling around. Okay, and the jiggling around is because of some small fluctuation. But those small fluctuations are large enough. Once you get to the Rydberg state, they can break up the whole thing. So you don't want that. And that's why you turn this thing off, do the Rydberg operations and put it back on again.
That is what the binding energy is for the electron, right?
Yeah. But you don't want the atoms to ionize either. I mean, it has to be a neutral, remain a neutral atom. If it is ionized, then it is lost from the whole process. And something else which people do is multiple 2-qubit can be performed simultaneously in different parts of the array, and that is useful because it can create highly entangled states. All you have to make sure that these things are in some non-overlapping region, but you can, this is So now comes the operation, which designed using certain pulses. So first step is to choose some scheme, pulse frequency, so that 0 can be with some label, whatever it is. And because the two hyperfine levels, whatever you call 0 and 1, are distinct in energy, you choose the pulse frequency for excitations, which can be in multiple steps, whatever it is. So one of them can be excited, but the other one can't be excited. Because the frequency tuning is actually quite sophisticated, and it can be carried out in very high precision. So what are used as a something called a dye lasers. That you want lasers which can offer a whole range of tunable frequencies. You want to decide the frequency according to your specification, and these were discovered maybe now 50 years back or so, something called a dye lasers, because they are based on organic molecules which essentially are the same as the ones which make dyes. And as you kind of remember, they make all kind of colors, and that flexibility to change colors is nothing but flexibility to change the frequency. And these are available. You tune everything so that two states are there. One of them gets coupled to R, but the other one cannot couple to R. That is a computational space in which you are going to work. And now apply three pulse sequence which is something similar to what went wrong in the other one. The pi pulse on the control qubit, then 2 pi on the target qubit, and then pi again on the control qubit, and to achieve the operation which is negative of control Z. Minus sign is just a overall phase. So now you have to see this, you have to again make the 4-state table and work out the algebra. So what does this pi pulse takes it's some specific frequency. It's applied on the here only on the control bit, but the job is it will take 0 to R and don't do anything to one state. Then the 2 pi pulse, it will fail due to Rydberg blockade. And control pulse has if the first control pulse succeeded in putting the states to R, then the 2 pi pulse on the second one will fail because of the Rydberg blockade. You just cannot take this target bit from whatever its original value is to a Rydberg state. Not possible. So now we can work out what will happen if suppose you start with the state 0, 0. Then you shine the first pi pulse, it will take that to R. Then the second one, which is on the target, you tried the 2 pi pulse over here, it can't go because the first one has already blocked that particular state. And then the second pi on the control will apply another pi which will bring R back to 0. So this it essentially is 2 pi on the control because this middle one fails. And the 2 pi rotation for this whatever two-level system which produce a minus sign. Okay. Then you try all the 4 things you have to try out, whatever it is. Easier to see what happens because if this is in state 1, these control pulse are going to fail because this cannot get excited, and the result is that in this particular case there is no Rydberg excitation. There is a 2 pi on the target, but that is also not going to do it. Is all pulses fail, and it does give a the state which is 1, 1. Okay. I mean, as I said, the answer is minus the control Z. So this 1, 1 is not going to change, and all the other ones are going to flip sign. Okay. So now let us ask what will happen in these two particular situations. That let me take this 1, 0. Okay. This control value is going to fail because it can't do anything to 1. But this 0 responds to the Rydberg excitation. But that is a 2 pi rotation. Okay. So this pi control fail, and this 2 pi target gives the 2 pi again, so it will flip the sign. Okay. And this last one, 0, 1, the 0 will go to R, but this 1 doesn't respond to this 2 pi pulse at all. It's in the wrong level, so it doesn't do anything, and so it behaves essentially the same way as the first one, such a 2 pi control applies, giving minus 0, 1. So that is essentially the implementation. You take advantage of this blockade that simultaneously you can't have two atoms in the R state, and whatever is done within this radius, some 2 to 3 lattice sites, on that radius you can apply control Z. Yeah. Because they are not connected. Nothing will connect to the R state. Only 0 state can be shifted to R. The other ones are mismatch. One cannot go anywhere by applying any of these pulses.
So this 2 pi control doesn't affect the one state, right?
Hmm?
The 2 pi pulse
Yeah.
doesn't affect the one state.
Yeah, it affects in this particular combination.
Right.
Yeah.
What about the second case? Could you explain that?
Second case, the first 0 response going from R, and nothing happens in the middle, and the other one is other pi, so it comes back to 0 with a negative sign. Why nothing happens to 1? Because this one is in the wrong frequency level. Yeah.
Where does the phase come from?
Because of the 2 pi rotation on a qubit gives a minus sign.
The pi and the
Because there are 2 pi, one is here, one is here, you add them up.
so it's 2 pi and the pi.
And this is kind of simple enough that there is an interesting extension of this scheme possible. and that application of control square Z gate, which related to the Toffoli gate, which is used quite often in reversible computation. It's a 3-qubit gate, but the point is that you can adjust this atomic array size to up to a certain distance. So if you get 3 qubits within the same region, you can apply a 3-qubit operation directly. And this is possible with five pulses. Not too complicated. If you want to break it down into quantum operation, it's actually quite cumbersome, but here it works. And I will write down the answer. It's kind of straightforward. It is kind of symmetrized version of what we did here. And yeah, I have used the 0 as a kind of state where something happens. Well, it's a notation, you can relabel it whichever way you want, but it's fine. Typically, control notation use that if it is 1, something happens, and 0, nothing happens. But it's a convention, whatever it is. Doesn't matter too much. But here now, you applied pi pulses on the two controls, then you apply something on the target, and then again the pi pulses on the two controls. So what happens is if the two states, if there are zeros over here, then it will get excited to the Rydberg level, and then the target state will respond or not respond depending on what its value is. And it's a Z, so if it is 0, it can respond one way. If it is 1, it can respond other way. And if it doesn't respond, all these pi pulses will get squared and you will get a minus sign. It will again work out with various combinations. The only different part is that you will get two minus signs, one on control 1 and another one on control 2. So this actually produces control square Z and not minus control square Z. Okay. So you just have to write down all the 8 possibilities and see what all will go through. Sometimes this will act, sometimes this will not act, and there will be only one situations where something will work, and that will flip the sign when both the control bits are in this 1-1 situation. So yeah, what will happen in that case is the state which is 1, 1, 0, it will flip sign, and then state which is 1, 1, 1, nothing will happen to it. And that is, well, it's minus z gate, 0 changes sign and 1 doesn't, but the point is, if it is 0, this 2 pi target will do something, and otherwise it won't. So you can work out that only 1, 1, 0. Yeah, so that, yeah, my time is up. So that's about it. This is how this Rydberg blockade is used to implement this elementary 2-qubit gates or even 3-qubit gates in a rather simple manner. With number of pulses is not that large. You can easily implement them, and the durations are all decided by how much you need to get a value of pi. So energy levels are all known, and you work out the duration so that the delta E multiplied by the duration is equal to pi. And the point of doing this is all this have to be reasonably fast, and because otherwise this atom will fall out the trap, but the time scale is in, so this can be, these operations can be managed in microseconds. So before all the other stuff can destroy various things, you have to finish this logic and carry out whatever steps of the algorithm. Okay. Yeah, so this is essentially the digital part of the Rydberg story, but there is a complement which is the analog part, and that also has been heavily studied. It's coming from the fact that you can arrange many of these atoms in the trap. You can actually make a 2-dimensional, 3-dimensional lattice. So now you can imagine that lattice is actually some physical model of quantum statistics, like a Hubbard model or some spin array or something like that. And it has a particular interaction coming from the Rydberg blockade. So the analog mode is you initialize a state and then just let it evolve and watch what kind of a complicated dynamics will be created, and that also has important uses in understanding many phenomena. That part will come in the next lecture, whatever it is. Yeah, so meanwhile, I can also tell you that next week is the last week for the lectures, and the topic I will add to all these things is what is called a measurement-based computing. which is not based on any logic circuits, but by just preparing some carefully designed initial state and performing only measurements. And it has become a important part of quantum optics. That all you do is perform a sequential set of measurements, sequential set of single qubit measurements, not even 2-qubit measurements, and it will solve some algorithm. It's a completely different structure compared to logic circuits, but it's completely equivalent. Whatever you can do in the logic circuit scenario, you can also do everything by just making measurements. And when it came as a completely unexpected concept, but yes, it can be proved that yes, everything is within a completely controlled situation and people are making those devices. So that's a different story, and that's the last topic I will consider. I'm not going to discuss the major focus of the industry, which is the superconducting quantum devices. So there probably you have seen various things in various labs and you already know how several things work, but I won't have time to go through that part of the story.
So, in control circuit, only 111 should flip signs among 8 possibility. Why here 110 flips?
That is what this pulse sequence will produce.
So we can
Okay.
we should interchange the interpretation of the event.
You can relabel things according to whatever convention you want. That is not a problem. You can say that instead of applying Z, you have applied minus Z. That is fine, but that does not cause any problem in terms of logic. What is?
110 will give the sign, but that would actually be multiplied with the previous result. If you take the 2 out of the equation, you get this.
Yeah, it will flip the sign set, but see here there will be 2 pi on C1 and 2 pi on C2 both occurring simultaneously, and each one will give some minus sign. So there will be -1 on C1, -1 on C2, multiply together, it disappears. Those kind of things you have to keep track of.
That one will be like because you're doing control 1, but then you cannot use pi C1 and pi C. Like 2 pi C1 and control 2. But the 2 pi pulses take the control pulses.
You have to use all these 5 pulses and ask what is the response of all 8 possibilities. Work out whatever is necessary.